So let's describe these orbitals a little bit more. The orbits in the Bohr model we specified with a number, a quantum number, n equals 1, 2, 3, 4, 5. And so we do the same thing with the orbitals, and that's called the principal quantum number. And it specifies the principal shell or the principal level of that orbital. And those numbers are, again, 1, 2, 3, 4, etc. As the n increases, the energy of that orbital increases. Then we also designate a letter, and the letter tells us which subshell that orbital is, and that is related to the shape of the orbital. And those are designated with letters, and the possible letters are S, P, D, and F. And you might say, well, 1, 2, 3, 4 was really nice. Why didn't we do A, B, C, D? Well, those letters actually have historical meaning. I keep thinking I need to look up what S meant because I don't remember. But P was for principal, D was for diffuse, and F was for fine. And those were descriptions of the spectral lines of the elements in their emission spectra. So there is a meaning behind them, and then we had been using them, and so they just kind of stuck. So I'm sorry, but you'll have to remember those 4 letters, S, P, D, and F. So let's look at the lowest energy orbital. That's in the lowest shell. And the Bohr model is a little bit helpful because we can still kind of use it to have some idea of what's going on with this quantum mechanical model. You can think of the atom as being a little bit like an onion where you can peel layers off. And so the layers of the onion skin would correspond to those principal shell levels. And so the 1s orbital is in the lowest shell. It's closest to the nucleus. It's lowest in energy. It's important to remember that orbitals are 3-dimensional. It's not a flat circular orbit. And one way to represent orbitals is with a dot representation. So this, you can imagine if we're taking a photograph of an electron, which we can't do, but imagine. We take a photograph every second for 10 minutes. Okay, and so, one time it's here, and one time it's here, and one time it's there, and one time it's here. So we get this distribution then of where the electron has been during those 10 minutes. And we see that most of the time the electron was in this middle region, and then it didn't go out here much at all. It's a little bit like, let me just pull up a blackboard here. So I have a 4-year-old, his name is Andrew, and he's a character. He just cracks us up all the time. But let's just imagine, this is roughly the shape of my house. And let's just imagine that Andrew's at home. I'll use red because that's a color of caution, right? And we just took a picture or marked on this little map of my house where he was, let's say every 5 minutes. And so the first time you maybe find him sleeping on the floor next to my bed. And then later he's still sleeping on the floor next to my bed, but he moved over a little bit. And then he might be in here eating breakfast, and then he had to go to the bathroom. He likes my bathroom because his brothers use the other one, and it's not very nice. And then he might be over here watching TV, and he never sits still, and so maybe he was over here, and then he came back here and he got a drink of water, and then he'd go to the bathroom again. And then he was over here looking at a bug in the dirt, right? And so we would see that this is actually his room over here. He goes there once in a while. And sometimes he goes out and plays in the driveway. We would see that we would find some areas where you're more likely to find Andrew. Okay, you're not likely to find Andrew in Zach's closet. He never goes in there. For one thing, it's so packed full of junk that you can't even get in there. But this is the idea of the electron in that distribution map. It's like, okay, well, we're taking pictures, and sometimes maybe you catch him walking down the hallway. And then there's that time when he was 2, and he stole the neighbor's big wheel and drove it 3 blocks to his uncle's house. He seriously did that. That one did scare me. So, probably 90% of the time, if we're home, he's actually on the property. But he's also been found across the street in his diaper with a soccer ball and long soccer socks. Just a diaper, no pants, just the diaper and the soccer socks pulled up to his thighs. And the soccer ball. Going to play in the dirt lot across the street. Who knows what is going on in that little brain of his? That could be scary to find out. But Andrew is a little bit like an electron. You can't really predict what he's going to do next. Sometimes you have an idea, and we can see that most of the time he's going to be in certain locations. Those are good places to look for him. But he might not be there. And so that's how an electron is. So when we're looking at, go back to that, so this distribution, this dot representation is a little bit like Andrew in the house, okay? Most of the time the electron is in this region, but it doesn't have to be, okay? The other thing about electrons, which your book doesn't really go into, but is just kind of fascinating, is you can know where they are, or you can know how fast they're moving, but you can't know both at the same time. It's very, very strange. And so if you like particle physics or something, you'd be interested in investigating that further. So we can represent orbitals as these dot representations. We can also represent them as geometric shapes. The s orbitals are spherical, so they're shaped like a ball. And so we can illustrate the shape of it like this. Now, it's important to understand that this is not a container, okay? This is not saying that the electron is inside of that. That's a representation of the distribution. And so we expect the electron would be found inside of that volume 90% of the time, but 10% of the time we would fully expect it to be outside. Okay, so we could superimpose the dots on top of the geometric shape. And so we see that some of these dots fall outside the actual shape. And go back to the shape. That's the shape, and there's the dot representation on top of it. So either of those ways are good ways to represent these orbitals. It's just a region in which the electron probably is. What is the electron doing inside that region? How is it moving? We can't really say. Okay, there's a lot of very hairy math that you can do, but even that doesn't really describe what an electron's doing. So he's just in there, bopping around. So if we have a hydrogen atom has one electron. That one electron, under normal circumstances, is going to be in the lowest energy orbital that it can be in. This is a little bit like teenage boys. I have some experience with teenage boys. Now I'll pick on Zach, because he's not here. Zach's favorite position, and the one you're most likely to find him in, is horizontal with his phone in his hand, right? And so he gets up and he does things. He gets up and he used to play football in high school, and he'd go play football. Expend tremendous amounts of energy, and then he'd come home and flat. He'll get up, flat. He always returns. That's his ground state. That's his preferred place. It's a low energy place. And electrons do that as well. They will sometimes move to higher orbitals, but then they always return to their lowest energy state. All of nature is driven by things going to lower energy. That's why things fall down instead of falling up. They have lower potential energy when they fall down. So we call that the ground state, the lowest energy state. And the electrons, like teenage boys, are going to seek out that low energy state whenever they can. But if you put energy into the atom, you can have the electron absorb energy, and then it will jump up to a higher state. That's called an excited state. The excited state is unstable. The electron will go up there, it's excited, it's going to go do something, and then it's done and it goes back to the ground state. Okay, just like Zach. He gets up and does stuff and comes back to the ground state. We did FaceTime with him the other night, and where was he? He was in his bed. So all atoms have one ground state with all of their electrons in their very lowest energy. But they have multiple excited states. They could be excited to different levels, and the electrons can go into different places. So the principal shell, n equals 1, has one subshell. The next shell is n equals 2, and that one has 2 subshells. So a shell is a little bit like a level. So the first level has only the one sublevel. The second level has 2 sublevels. It's a little bit like a hotel. So the n equals 1, 2, 3, those would be like the floors of the hotel. The first floor only has 1 room. The second floor has 2 rooms. The third floor has 3 rooms. Okay? So on the first floor, if you're in principal shell 1, you have to be in that S room. Okay? You have to be, because it's the only place they can be. On the second shell, on the second floor of the hotel, there's 2 rooms, and you could be in either one. One is the S subshell, and one is the P subshell. The S subshell on the second level, second shell, looks very much like the 1s. The difference is that it's a little bit bigger, and it's higher in energy, but it's the same shape. All the s orbitals are shaped like a sphere. So the 2s orbital is bigger than the 1s, and the 3s is bigger, and the 4s is bigger. And so you can kind of imagine them as just concentric spheres. So there's, yes, I know this. That's the S subshell. On that second level, there's a second subshell. In the hotel, there's a second room. This is the P subshell, and this P subshell actually has 3 different orbitals in it, and they have a very different shape. Most books describe them as being shaped like a dumbbell. Kind of looks like 2 balloons. So this is 1 orbital, and so this geometric shape describes where we can expect to find an electron 90% of the time, one that is residing in this P orbital. Here's the dot representation, and we see that most of it's in this little region here or in this little region here. So that's 1 orbital, and another orbital, because there's 3, is the same shape, but it's oriented differently. So these are X, Y, Z axes representing 3-dimensional space. And then the third orbital is the same shape, the same size, but oriented differently in space. So in the hotel analogy, the orbitals are like beds. So the S room has 1 bed. It only has 1 orbital. The S subshell has 1 orbital. The P subshell has 3 orbitals. The P room on the hotel has 3 beds. Okay? The beds are the same size. They're all double beds, but they're just in different places in the room. So here's another way to represent this organization, and this is where it looks a little more like a hotel, because you can imagine that this is the first floor of the hotel, and there's 1 room, and here's the second floor, and it has 2 rooms, and the third floor with 3 rooms, and the fourth floor has 4 rooms. Guess how many rooms the 5th floor has? 5. Yeah, there's a pattern here. So the number of subshells equals the number of the shell. The third shell has 3 subshells. That one level is divided into 3 sublevels. So that third shell has 3 sublevels. They're called S, P, and D. We talked about the S and the P, and they're the same shape as in the 2 shell, n equals 2. But again, they're larger, a little bit larger, and they're higher in energy. The D has 5 orbitals. So the third floor of the hotel has the S room, the P room, and the D room has 5 beds in it. That's like a suite. That would be great for my family, because we could go to Disneyland and just rent 1 hotel room instead of 2. That really ups your price when you have to double up on hotel rooms. These are the shapes of the d orbitals. How's that for weird, huh? So there's 5 of them. 4 of them have the same shape but are oriented differently in space. These look like 4 balloons with their ends kind of tied together or something. So these 4 are oriented differently in space, but they have the same shape. And then the 5th one is really weird, and it looks like 2 balloons wearing a life preserver or something, with this donut around the middle. I'm not going to make you draw those shapes. Okay? I think there's a homework assignment that asks you to at least recognize the shapes, but that's about it. So those are the d orbitals. So we have some shorthand ways of representing how the electrons are arranged in atoms, and one of them is called an electron configuration. It just shows us which orbitals are occupied by electrons, how many electrons each of them have. And so if we look at the ground state for hydrogen, hydrogen only has one electron. 1s is the lowest energy orbital. It's the first level, n equals 1. N equals 1 only has one sublevel, it's the s sublevel. And so this is the designation for the orbital, 1s. And then as a superscript, we indicate how many electrons are in that orbital, or in that subshell. So this is 1s1. So for hydrogen, it only has one electron, it's in the 1s orbital. Another way to represent this is with an orbital diagram. Here we're showing the orbitals as boxes. So this looks a little more, oops, I touched a button. Looks a little more like the hotel idea. So this is representing the bed. Okay, and so we have one person sleeping in the bed. We represent the electrons as arrows in an orbital diagram, and the orbitals are boxes. So for hydrogen, it's 1s and it's got one arrow in it. So the direction of that arrow actually has some significance. It turns out that electrons have a property that we call electron spin. And I think the easiest way for you to think of that is that you've imagined the electrons spinning. Okay, and some of them spin clockwise and some of them spin counterclockwise. It's a fundamental property of electrons that they spin. Okay, and that's just it's just to help you think about it. So don't go on and take, advanced P-Chem classes and come back and say, you're wrong, they don't actually spin like that. It's just to help you understand. So just think of them as spinning. So some of them spin to the right, some spin to the left. And the Pauli exclusion principle says that orbitals can have no more than 2 electrons in them, and they have to be of opposing spins. So we symbolize these in that orbital diagram as being arrows pointing in different directions. So one arrow pointing up and one arrow pointing down means that we have opposite spins. So let's write electron configurations and orbital diagrams for helium and lithium. So we'll do helium first. Oops, that won't work. Helium. In order to do an electron configuration or diagram, we need to know how many electrons the atom has. And so we look at the periodic table and we see that helium is element number 2. That means it has 2 electrons. I personally think when you're starting out that the orbital diagrams are a little easier to understand. And so let's do that one. So we envision that hotel, and the lowest room is that 1s. So in the hotel analogy, energy would correspond to money. And when you go to a higher energy level, it's going to cost you more money to stay in that room. And so the electrons want to go to the low energy level. The people want to stay in the cheap rooms. And those are the ones down on the ground floor, where you might have people breaking into your window or something. I don't know. So 1s is the lowest orbital. And that can hold 2 electrons. A bed can hold 2 people, right? So we're going to have one arrow pointing up and one arrow pointing down. That's the orbital diagram for helium. It shows that there are 2 electrons in the 1s orbital, and they have opposite spins. And yes, this is all very weird, isn't it? It's like learning some strange code or how to play Dungeons and Dragons or something. That's the orbital diagram. The electron configuration would be 1s. That's the lowest orbital, lowest energy, and that has 2 electrons in it, so we give it a superscript 2. So 1s2. So try to stay with me, and hopefully by the end of the class period it'll start to make sense. The next element is lithium. Lithium has 3 electrons. So if we're going to draw the orbital diagram for lithium, there's that 1s orbital. That can only hold 2 electrons though. So we can put 2 electrons in there, but lithium has 3 electrons. That orbital is full. The 3rd electron has to go to a higher energy orbital. The n equals 1 shell only has that 1 subshell, the s. So the first shell is full. We're going to have to go up to the second shell, which is 2, and the lowest energy one there is s. Again, they go s, p, d. So we can put 1 in there. So in the hotel, that ground floor room that was the cheapest is full. The next person coming in has to go to the 2nd floor and take the next most expensive room. Because they're really serious when they say 2 people per bed. So then how do we indicate that as an electron configuration? Well, 1s, that box has 2 electrons in it. And 2s, that one has 1. So the electron configuration for lithium is 1s2, 2s1. Any questions so far? Yes. When do you use the D and F and the P's? When you get more electrons. Yeah. And there's another diagram coming up that'll help us to understand that. Any other questions? This diagram. Yes, question?
So when the first one is taken, we have to move to the second box?
Mm-hmm.
Okay.
And so this diagram actually is a lot more helpful, I think. I should maybe do this one first next time I teach this class. So here's the first level. Each of these lines is representing an orbital. So you could put 2 electrons in each of these lines. Let's do that. We'll make the electrons be blue. I don't know. Okay, so this one, we could have 1 spinning up and 1 spinning down. That's the lowest energy. When you have another electron, it's going to have to go into the next higher level. There's room for 2 electrons there. When that's full and another electron comes to the hotel, they've got to go to the next room. The next room is over here. This is the next highest. So this is energy. This is like the cost of staying in that room. Can't even point today. So as you go up, it's going to cost more. So then the next electron would go here. And so you can imagine then, we're filling up, we'd fill up these 3 orbitals, and then we'd have to move up to this subshell. The n equals 3 shell has s, and there's the 3 p orbitals, and then there are 5 d orbitals. And we're not going to show the f's. Does that help a little bit? A little bit? This is weird stuff. Yes?
So on the 2p, can you put another electron right there, or it just has to be 1?
This could end up getting completely filled up, and we'll talk about...
It's just 1 over.
So this is how they're going to fill. And we'll talk about why these would go in separately like that first in a minute. But they're just going to fill in order. So as we're looking at the periodic table and you're going from hydrogen to helium to lithium to beryllium, they each have 1 more electron. And so each one is just adding 1 more electron to this diagram. In hydrogen, where we only have 1 electron, all of the orbitals in the second level would have the same energy. So the 2s and the 2p orbitals would all be the same energy. But that's only true in hydrogen. In all the other atoms that have multi-electrons, the energy levels get kind of shifted around like this because of interactions between the electrons. So because of how the electrons interact, the s orbital in the second level is lower in energy than the p. And in the third level, the s is lower than the p, and the p is lower than the d. So they get a little spread out that way. Let's do the electron configuration and the orbital diagram for carbon. So carbon, how many electrons does carbon have? 6. 6 electrons. Let's do the orbital diagram first. So the lowest room is the 1s, and then next is the 2s. And in orbital diagrams, what we do for the p is we put 3 boxes together. That's the p. So this is the room on the first floor, and this is the second floor, and it's got a room with 1 bed in it. And also on the second floor there's a second room, and that one has 3 beds in it. And so then we're going to put the little electrons, the little arrows, in their beds. Yes. If I think what goes on in Andrew's head is weird, what goes on in my head must be really, really weird. Because I actually think about it like this. It's kind of scary. So what are the electrons going to do? Well, they're cheap. Okay, so they're going to take this first one, going to fill it up. 2 electrons go in there. They get the lowest price. They're happy. The next ones have to move up to the next more expensive room, the next higher energy orbital. So we've got 4 electrons taken care of. We've got 2 that are going to have to go into the next room. And so what they're going to do, so 1 takes that bed. So you've got 2 electrons in an orbital, in a subshell with 3 orbitals. You've got 2 guys in a hotel room with 3 beds. Are they going to sleep in the same bed together? No way, okay? Or it's like getting on the bus. When I was in college, I rode the bus. And you get on the bus, and if there are empty seats, you do not sit next to a stranger, right? You don't. You go sit by yourself. Once all the empty seats are filled, then it's perfectly fine to go sit by a stranger. Everybody understands, well, you can't sit by yourself, you have to sit by somebody, so you pick the least scary person to sit next to, right? So 1 electron goes in here. The next electron is not going to go into the same orbital with the first electron. He's going to take an orbital to himself. And this is what Hund's rule tells us, is that when we're filling orbitals of equal energy, and those p orbitals have the same energy, we're going to fill them singly first with parallel spins. So we're going to put them all in with up arrows, and then if we have to, we'll come back in and fill in with down arrows. So that's our orbital diagram. And then to write the electron configuration, we're just going to, it's kind of a shorthand, we're going to tally up who's where. So in 1s, there are 2 arrows, 2 electrons. In 2s, there's 2 electrons. And in 2p, there's 2 electrons. So I kind of envision this electron configuration as being what the guy at the front desk's writing down, because he needs to keep track of where the people are staying, right? And so, you come in and you're like, oh, well, there's room in this room, so you can go in there, and then he'll change the number. So he knows where everybody is. So that's the electron configuration for carbon. Any questions? Does this make any sense at all? A little bit? So the orbitals fill in this order. Let's go back to this for a minute. We see that the 1s is lowest, then 2s, then 2p, then 3s, then 3p, and that's where things get a little wonky. We would expect 3d to be next, but 4s is actually lower in energy. And then 3d, and then we go back to 4p, but then 5s squeezes in here before 4d. And we have to figure out, how do we remember these? Well, one way to do it that students generally like is you can make a table like this. So you see this is like stair steps, right? So we've got 1s and 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f. And this one would also have another one over here, but we're not going to go there. So there's a pattern there. You make that little grid, and then this is the filling order. You start up here. Oops, what am I doing? You start here. I'm trying to draw, and it's not drawing. Maybe if I turn it sideways. Well, it draws over there. Okay, so we're going to draw down this way, and then we're going to go back up and come down 2s, 2p, 3s. We jump back up here. After 3s is 3p, but then 4s gets in there. So you see what I'm doing? I'm just following that line. Not very well. This is harder than it looks. Yeah, that's lovely. But that's the order. So that's one way to remember it. 1s, 2s, 2p, 3s, 4p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s. Isn't that fun? Have a good weekend.